So I believe what we are supposed to be talking about today is second order passive filter circuits. Scroll up here. And I'm going to pre-apologize if you start to hear a loud grunting noise. That is my tiny dog snoring. The dog is currently laying in her bed and staring at me. All right, so second order passive filter circuits can be used to realize low pass filters and high pass filters, just like our first order filter circuits. But they can also provide more interesting responses by giving us the band stop filter and band pass filter. So the first one that I want to look at is this guy, where we have an inductance J omega L in series with a capacitance 1 over J omega C in series with a resistance R. And we're going to take the voltage drop at the output to be the voltage over our resistor. So on our left-hand side, we have our input voltage as a function of frequency. And on the output side here, or on the right-hand side, we have our output voltage as a function of frequency. So using our voltage divider technique, we can easily see that the transfer function for this circuit is just going to be H of omega is equal to R divided by J omega L plus 1 over J omega C plus R. And to simplify things, I'm going to multiply by a factor of J omega C over J omega C. And that's going to get rid of the fraction in my denominator. And what that's going to leave me with is J omega RC in the numerator, 1 minus omega squared LC as the real part of my denominator, and J omega RC as the imaginary part of my denominator. Okay. So from here, we can go about figuring out what the magnitude is and the phase response and all that kind of stuff. But before we do that, I want to talk about how to find our center frequency, omega naught. So for a filter, omega naught is the frequency at which the transfer function H of omega is purely real. So that means that all of the imaginary parts effectively cancel each other out. So if we look at this guy, we have a factor of J omega RC in the numerator, and then there's another J omega RC in the denominator. So if the 1 minus omega squared LC bit goes to 0, we'll have J omega RC over J omega RC, which is just 1. So our transfer function would be purely real. So from that, it should be fairly obvious to see that omega naught is going to be the square root of 1 over LC, which is exactly what omega naught was for a series RLC circuit, because they really represent the same thing. So from here, now that we know what our center frequency is, we're going to need to determine our magnitude response in order to figure out what omega C1, our low frequency corner frequency is, and omega C2, our high frequency corner frequency is. So we can expand our transfer function doing the exact same thing that we did in class on Wednesday, where we're just going to multiply our transfer function by the complex conjugate of the denominator and divide by the complex conjugate of the denominator as well. So we're going to have 1 minus omega squared LC plus j omega RC in my denominator, j omega RC in my numerator, and we're going to multiply this guy by 1 minus omega squared LC minus j omega RC over that same value. And if we perform that multiplication, in our denominator, we're going to have a factor of 1 minus omega squared LC quantity squared. And we're going to have plus omega RC quantity squared, where the cross multiplied terms cancel each other out, and the fact that we have a negative j times a positive j is giving us the 1 that's in front of the omega RC quantity squared. In my numerator here, I'm going to have a real part that is j omega RC times negative j omega RC. So that's going to give me omega RC quantity squared. And then for my imaginary part, just putting my j out front here, I'm going to have that same denominator, 1 minus omega squared LC quantity squared plus omega RC quantity squared. And I have a factor of omega RC multiplied by 1 minus omega squared LC left over. So this is my rectangular form representation of my transfer function. And before we go any further, does anybody have any questions about how I got to this point? All right. So our magnitude is going to be the square root of the real part squared so there's my denominator, here's my numerator, and then I'm squaring this whole fraction plus my imaginary part squared. So again, here's my denominator. And here's my numerator. square this guy, and all of this is underneath the square root sign. And it should be fairly obvious that we are going to have a denominator of 1 minus omega squared LC squared plus omega RC squared and our numerator. So we're going to have a factor of omega RC to the, we'll write this down and then we'll do some factoring here. So we're going to have omega RC to the 4th power plus, omega RC squared times 1 minus omega squared LC quantity squared. And we can factor out a common factor of omega RC squared from this. So my denominator is going to stay 1 minus omega squared LC quantity squared plus omega RC quantity squared all squared. If I factor out an omega RC quantity squared, this is going to be multiplied by one minus omega squared LC for quantity squared for my second term plus omega RC quantity squared for my first term. And this guy right here cancels out one of my powers in my denominator, leaving me with the square root of 1 minus omega squared LC squared plus omega RC squared in my denominator, and just a factor of omega RC in my numerator. So let's do our kind of simplified analysis to figure out what the response is doing here, to figure out what kind of filter that we have. So at, let's see, the magnitude of H at omega is equal to 0 should give me what? Anybody?
0.
0, yeah. So our numerator is going to look like 0 and our denominator is going to look like the square root of 1. So just plain old 0. For very high frequencies, when our magnitude response, we're looking for our magnitude response at omega is roughly infinity, what does this guy simplify to?
Also 0.
Also 0, yeah. So we're going to have effectively infinity over the square root of infinity squared is also 0. So from this, we can see that very low frequencies are being attenuated and very high frequencies are being attenuated, which means that this guy is a band pass filter. So for our band pass filter, our corner frequencies, omega C1, and I'm also just going to call this omega low. This is still just when our magnitude response is going to be equal to 1 over the square root of 2. But we're going to have two values that satisfy that constraint now. Our first one is negative R over 2L plus the square root of R over 2L squared plus omega naught squared and omega C2, or our high frequency corner frequency, omega high, is going to be positive R over 2L plus the square root of R over 2L quantity squared plus omega naught squared. So very, very similar, a little different, but very, very similar to what our natural frequencies were for our series RLC circuits. Okay, really just the placement of a couple of signs change. Oops, not too far. So before we move on to the phase response, any questions here? All right. So for our phase response, theta h of omega, that's going to be the inverse tangent of the imaginary part, which I need to look up here real quick. Omega RC times 1 minus omega squared LC. Omega RC times 1 minus omega squared LC divided by that denominator that was 1 minus omega squared LC squared plus omega RC squared. This will be divided by omega RC squared over that same denominator and let me just make sure what's going on in the chat here. Jared, are you asking where the class is?
I meant to set that as a DM.
Okay. I'm at my house because classes were moved fully online today. Did you not get the email that literally everybody at the university got?
I was meeting with my advisor like 20 minutes ago.
I'll tell you, but all classes are supposed to be fully online today.
Okay.
I'm at home. All right. I thought I was your advisor. Oh, you're talking about your physics advisor. Anyway, all right. Goodness gracious. Okay, making sure I got all that done correctly. So obviously these denominators cancel each other out. And this is going to leave us with the arc tangent of 1 minus omega squared LC divided by omega RC as our phase response for our bandpass filter. So anybody have any questions on our bandpass filter equations? Because I'm going to ask you guys to design one as both part of your upcoming take-home test, as well as a design project. All right. So let's look at another circuit then. Still just going to be a series RLC circuit for all intents and purposes. So in the last circuit, we took the voltage drop over the resistor. Now we are going to take the voltage drop over a combination of the capacitor and the inductor. So this will be J omega L. This is 1 over J omega C. Here's our input voltage quantity. Here is our output. And from this, using simple voltage divider rules, We can see that our transfer function is going to be j omega L plus 1 over j omega C divided by R plus j omega L plus 1 over j omega C. And to clear our fractions, we're again going to multiply by a factor of j omega C over j omega C, which gives me 1 plus omega squared LC in my numerator and 1 plus omega squared LC plus j omega RC in my denominator. Let me just double check that math here real quick. So that seems, so that's where the 1 comes from. J times J, actually, these should both be negative. I thought. Yeah, because I have a positive J times a positive J, which is giving me a negative 1. Okay, sorry. So it should be fairly obvious here that when omega is equal to the square root of 1 over LC, our transfer function becomes purely real again. So we have the exact same omega naught, 1 over root LC. We can now break this down into its constituent real and imaginary parts by once again multiplying by the complex conjugate of the denominator over the complex conjugate of the denominator. 1 minus omega squared LC plus j omega RC 1 minus omega squared LC up here. Multiply this guy by 1 minus omega squared LC minus j omega RC divided by that same quantity. And in our denominator, we're obviously going to have a 1 minus omega squared LC quantity squared plus omega RC quantity squared term. Our real part of this guy is going to be 1 minus omega squared LC quantity squared. And our imaginary part is actually going to have a negative sign. It'll be negative j. And we're going to have the exact same denominator. And let's see, we're going to have negative j omega RC times 1 minus omega squared LC. So our magnitude is going to be the square root of the real part times the real part squared plus the the imaginary part squared. This whole thing squared plus this whole thing omega RC 1 minus omega squared LC square this guy, square root goes over the whole thing. And now we're going to have something very similar to what we had with the previous example, except that we're going to have a common factor of 1 minus omega squared LC squared that's going to get factored out of everything. So kind of jumping ahead to that step where we've already done the factoring, we're going to have 1 minus omega squared LC quantity squared plus omega RC quantity squared in our denominator. In our numerator, we're going to have a factor of 1 minus omega squared LC quantity squared multiplied by so let's see here. So that's to the fourth power. When I take that out, I'm going to have a 1 minus omega squared LC squared plus omega RC squared, like so. And this guy cancels one of our powers here, giving us 1 minus omega squared LC divided by the square root of 1 minus omega squared LC squared plus omega RC squared. So our magnitude response evaluated at omega is equal to 0 gives us what?
One.
1, yeah. And at infinity here, we're going to have infinity squared over infinity, square root of infinity to the fourth power, so that's effectively also going to be 1. And so we have a band stop filter where our corner frequency, omega C1 or omega low, is actually the exact same thing as we had for our band pass filter. So that's negative R over 2L plus the square root of R over 2L quantity squared plus omega naught squared, and omega C2 is omega high or positive R over 2L plus the square root of R over 2L quantity squared plus omega naught squared. So our band pass and our band stop filters have the exact same corner frequencies and center frequency. We're going to see now that our phase response, theta h of omega, is the arctangent of the imaginary part, which, let me find that real quick. Omega RC times 1 minus omega squared LC divided by, I'm just going to write down the denominator here. And for our real part, we had 1 minus omega squared LC quantity squared divided by that same denominator. These guys cancel each other out. This guy cancels one of these powers, and we are left with the inverse tangent of omega RC divided by 1 minus omega squared LC. All right, so these were the ones that the two filters that require two energy storage elements to achieve, right? We can't get a band stop or a band pass filter without having two energy storage elements. So without going through the full derivations and all that kind of stuff, I want to ask you guys for this circuit, here's our resistor R, here's our inductor J omega L, and here is our capacitor having an impedance of 1 over J omega C. This is Vn. And this is V out. What kind of filter do you think this is going to be? We actually shouldn't need to do really any analysis at all here to figure it out. All right, let me ask the question in a slightly different way. What does the impedance of the capacitor look like at very low frequencies? An open
Isn't
circuit.
it 0?
So the impedance is infinitely large at very low frequencies. So that means that all of V in gets passed to V out. At very high frequencies, the impedance of the capacitor looks like a short circuit, which means V out is effectively 0. So this is obviously then a low pass filter because it sends all of the low frequency signals through and attenuates all of the high frequency signals. So this is a low pass filter where our corner frequency omega C is going to be 1 over the square root of LC. And I'm going to make you guys give me the transfer function and all that kind of good stuff in a homework problem. What if we switch the position of the capacitor and the inductor? R 1 over J omega C. Here's J omega L. Here's Vn. Oops, goodness. Here's V out. So for an inductor, since it looks like a short circuit at very low frequencies, that means that V out is a short or is 0 volts at very low frequencies. At high frequencies, the impedance of the inductor starts to approach infinitely large, meaning that it looks like an open circuit, and therefore all of our input signal gets passed to the output. And from this, we obviously have a high pass filter, where again, our corner frequency turns out to be 1 over the square root of LC. So I'm going to wrap things up here with what I hope to be is a very simple question. All of these filter circuits that we've developed here, these first and second order filter circuits, are based on series RLC circuits. Why can't we make filters with parallel RLC circuits?
They effectively act like first order, wouldn't they? Because the voltage will be the same across them.
So you're kind of close, right? So if all of the elements are in parallel, they all have the same voltage drop over them. So if we had,
There'd be no gain, therefore it wouldn't be a filter. I mean,
yeah. Effectively, yeah. So if we have Vn, and then even a first order case where we have a resistor R in parallel with an inductor L, and this is V out. Vn and V out are always the same thing because there's a potential difference across elements that are connected in parallel. So filters don't work with parallel RLC circuits because we can't look at a portion of the spectrum. We always get the full input signal at our output, regardless of what the frequency is.
What about if you've got like one of the elements in series and then the other two are in parallel with each other? And take
So-
the voltage across the two parallels.
Yeah, so that would absolutely work as a filter circuit, but we can't just have everything full on in parallel, but 100%. And we're going to see, well, not we, maybe we actually, depending on who winds up teaching circuits 3 in the fall, some filter schemes like that have some elements connected in parallel and others in series to get responses. Absolutely. But those are typically going to look like higher order filters and all that kind of stuff. So, all right. So this is our crash course in an introduction to filters for circuits 2. Anybody have any lingering questions they want answered before we knock off for the day about 30 minutes early?
Could you go over real quickly how you determine if they were high pass or low pass filters when you're talking about the frequency?
Sure. So all I'm doing, it's the exact same thing that I was doing right here. Or are you talking about this specifically, Justin?
This specifically.
Okay. So let me write this. Okay. So the impedance of a capacitor at very low frequencies is infinitely large, right?
Yes, sir.
And the impedance of a capacitor at very high frequencies is 0. So if we're taking the voltage drop over a short circuit, what's that voltage going to be?
It's just 0.
Exactly right. So at very high frequencies, our capacitor attenuates all of the input signal because the output is forced to be 0 volts. At very low frequencies, where this guy just looks like an open circuit, V out is exactly equal to V in. So that's why we have a low pass filter response. At low frequencies, all of our input signal makes it to the output. At very high frequencies, none of our input signal makes it to the output. The exact opposite situation is happening when we take the voltage drop over the inductor. So what I mean by that is the impedance of an inductor at omega is equal to 0 is just 0. The impedance of the inductor at omega is equal to infinity is infinitely large. It's literally just the opposite case that we had previously, right? So for very low frequencies, V out is 0. For very high frequencies, V out is V in.
Oh, so after like everything up to a certain point is filtered out, so it would be a low pass filter.
Exactly right. So as the impedance of the, for the low pass filter, as the impedance of the capacitor gets smaller and smaller and smaller, the voltage that we see at the output gets smaller and smaller and smaller because of Ohm's law, up to such a point where we're at a frequency high enough to where the voltage drop over the capacitor is essentially 0. And then we're completely rejecting everything beyond that point. And again, the exact opposite is what's happening for our high pass filter with when we take the voltage drop over the inductor specifically. Any other questions?
May we see your dog?
Sure. Molly, come here. I'm gonna be pissed off that I'm getting her out of bed. Give me just a second. No, don't run away, butthole. This is Molly. She is a 13-year-old Maltese, and she snores like an adult human man.
I think she's blinking help in Morse code.
Maybe she is. She, since I have woken her up, she wants a treat now. So anyway. All right, you guys got anything else for me?
Would you be willing to scroll up to the first page? I was a little late because I was at work.
Yeah, not a problem at all, Alexis. Let's see. Tell me when to stop.
Just like the very first part, like the first 10 minutes of class. Yeah, right there.
Okay,
Appreciate it.
no problem.